Imagine for a second that you're a 17th century French lawyer.
Okay.
You spend all your days, settling property disputes, looking over dry contracts, dealing with all the local court bureaucracy.
That's pretty tedious, honestly.
Right. But then, on the weekends, just to relax, you retreat to your study and you casually lay the groundwork for calculus.
As one does.
Yeah, you invent modern probability theory, and you leave behind a math puzzle that is so impossibly complex, it takes humanity like over 3 centuries and supercomputers to finally solve it.
It really forces you to completely rethink what a weekend hobby can actually accomplish. I mean, we are talking about a man who altered the fundamental course of human knowledge.
Totally.
And he did it entirely in his spare time while holding down a very demanding full-time job.
It's wild. So we're drawing today from a comprehensive Wikipedia article on Pierre de Fermat. And our mission for this deep dive is to understand exactly how this provincial magistrate managed this.
Okay, let's unpack this. How does a guy who treated mathematics essentially as like a parlor trick completely reshape our understanding of numbers, physics, and chance?
Well, to really grasp the scale of what Fermat accomplished, we have to look at the environment he was operating in.
Right.
So he was born in Beaumont-le-Mans in southern France. Now, the historical record generally accepts his birth year as 1601.
Okay.
Though there is a fascinating little wrinkle in the research suggesting it might actually be 1607.
Wait, really? A 6-year difference?
Yeah, because he had a half-brother who was also named Pierre, who died in infancy.
Oh, wow. Which I guess sets a perfect tone for a life that is just surrounded by hidden details and missing information.
Exactly. And his background was entirely outside the traditional academic elite. His father was a wealthy leather merchant, so Fermat was steered toward a practical, respectable career.
Makes sense. He earned a bachelor's in civil law from the University of Orleans 1626, and by 1630, he purchased the office of a counselor at the Parlement de Toulouse.
Which was one of the high courts in France, right?
Yes, exactly.
And buying a government office, I mean, that was standard practice back then. It was a massive status symbol.
Oh, absolutely. He held that judicial position for the rest of his life, and that actually officially entitled him to add the aristocratic de to his name.
Ah, so becoming Pierre de Fermat.
Right. He was a serious man of the law.
But his mind was remarkably restless, apparently. The source mentions he was fluent in 6 languages.
Yes, French, Latin, Occitan, Classical Greek, Italian, and Spanish.
That is just, I can barely handle one.
I know, right? And he wrote poetry. He was actually so incredibly skilled in ancient languages that recognized scholars would seek his advice to help correct classical Greek texts.
But his true obsession, like the thing that really kept him up at night, was mathematics.
Always mathematics.
He never treated it as a profession, though, which is the crazy part. He never published big formal textbooks.
No, not at all.
Instead, his method for communicating his groundbreaking discoveries was just mailing letters to his friends.
Yep. And he would routinely send these letters with absolutely no proof for his theorems attached.
Just the answer.
Just the answers. He would simply state a massive, universe-bending mathematical truth and challenge the recipient to figure out how he arrived at it.
I kept thinking about this while reading the source material. It's like, imagine a brilliant modern software developer dropping 1,000 lines of highly complex, entirely uncommented code onto a public forum.
Oh, man.
And they just say, this solves everything, and then they just log off and walk away.
Yeah.
And everyone else is left agonizing over how the code actually compiles.
What's fascinating here is that while that sounds incredibly frustrating to modern sensibilities, we have to remember the context of European mathematical circles in the 17th century.
Okay, set the scene for me.
Secrecy was the primary currency. Knowledge wasn't freely shared, it was hoarded.
But why hoard it if you want to be recognized for your genius? I mean, don't you want people to know how smart you are?
Well, because mathematical prowess was often a direct path to royal patronage.
Oh, money and power.
Exactly. You proved your intellectual superiority by challenging other mathematicians to solve puzzles that you already had the answer to.
It's like a duel.
It is. If they failed and you succeeded, your stock went up. But Fermat's particular habit of dropping these unproven bombs naturally led to intense, sometimes really bitter priority disputes with his contemporaries.
Like René Descartes, right?
And John Wallis?
Yes, most notably Descartes.
Descartes, as in the famous, I think, therefore I am philosopher.
The very same. Descartes published a massive work integrating algebra and geometry. And Fermat, who's just operating quietly in his study, essentially said, yes, I've been doing this for years, and your methods are a bit clunky.
Oh, wow. just casually insulting Descartes. Descartes was furious. I mean, he called Fermat a braggart. They had a long-standing feud because Fermat was perfectly happy to keep the mechanisms of his math a complete mystery.
Leaving towering figures like Descartes just constantly guessing.
Exactly.
And the mechanism he was using, that's what truly set him apart. The source notes that he took ancient Greek treatises and combined them with new algebraic methods.
Yeah.
But how does that actually work in practice?
Well, think about how the ancient Greeks did math. It was heavily geometric. They were drawing physical shapes, triangles, circles, intersecting lines.
Right, literally in the sand or on parchment.
Yeah, it was highly visual. But physical drawings have limits. Fermat realized that you could take those physical shapes and represent them entirely with abstract algebraic equations.
So instead of drawing a circle, you write an equation that perfectly defines every point on that circle.
Precisely. He injected geometric shapes with algebraic life. And once a shape becomes an equation, you aren't limited by what you can physically draw anymore.
Because you can just change the numbers.
Right. You can manipulate the equation infinitely. You can scale it, twist it, explore its properties and dimensions you can't even see. This bridge between algebra and geometry is the foundation of modern mathematics.
And he was building it in his spare time.
Just for fun.
Which brings us to the actual math he was doing. Specifically, his work in number theory. The source material details how he studied perfect numbers, Pell's equation, and how he invented the factorization method.
Factorization is actually a great example of how his mind worked.
Okay, I need some help visualizing that. Because if I have a massive number and I need to find its factors, the standard way is just brute force, right? I just start dividing it by smaller numbers until something fits evenly.
Right, and if the number is in the millions, brute force will take you a lifetime.
Yeah, my calculator would just give up.
Fermat hated brute force, so he invented a factorization method using the difference of two squares. It was essentially an algebraic shortcut.
A shortcut how?
Instead of testing every single number, he looked for a specific geometric pattern within the math. He realized that any odd number can be expressed as the difference of two square numbers.
Okay.
By setting up a simple algebraic equation based on that rule, he could quickly crack massive numbers that would have taken other mathematicians weeks to solve.
So he was basically building cheat codes for reality.
Pretty much. And he also popularized a technique called proof by infinite descent.
Proof by infinite descent. It sounds like a sci-fi movie.
It's a brilliant logical trap. Let's say you want to prove that a certain mathematical condition cannot possibly exist.
Okay.
Fermat would assume, just for the sake of argument, that the condition did exist. Then he would prove that if it existed for a specific whole number, it must also exist for a slightly smaller whole number.
Oh, I see where this is going. And if it exists for that smaller number, it must exist for an even smaller one.
Down and down it goes.
Yeah.
He created an endless downward spiral. But because we are dealing with positive whole numbers, you can't spiral downward infinitely. You eventually hit zero.
You run out of numbers.
Exactly. So since an infinite descent of positive whole numbers is logically impossible, the initial assumption must be false.
That is a remarkably elegant way of proving a negative.
It really is.
And all of this brilliant, secretive work culminated in what became known as Fermat's last theorem. This is the big one. And he didn't even mail this one out to his friends to brag.
No, this one was entirely private.
It was found posthumously by his son. Fermat had literally jotted it down in the margin of his personal copy of an ancient math book, Diophantus's Arithmetica.
Yeah, Diophantus was a Greek mathematician who studied equations with multiple variables. In the margin, next to a specific problem, Fermat wrote down an equation of his own.
The famous one.
Right, that a to the power of n plus b to the power of n equals c to the power of n has no whole number solutions when n is greater than 2.
Which, when you look at it, looks just like the Pythagorean theorem, right? Yeah. A squared plus b squared equals c squared.
It's exactly the same format.
Which we know has plenty of whole number solutions, like 3, 4, and 5.
Mm-hmm.
But Fermat is saying the moment you change that squared to a cubed, or a power of 4, or a power of 5, it becomes utterly impossible to find whole numbers that make the equation work.
And then right below that equation, he wrote the most infamous sentence in the history of mathematics.
Oh, the margin note.
Yeah. He wrote in Latin that he had discovered a truly marvelous proof for this proposition, but that the margin of the book was simply too small to contain it.
The ultimate intellectual mic drop.
Yeah.
But look, I have to push back heavily on Fermat's legend here.
Go for it.
Did he really possess that proof, or was he just being unbelievably arrogant? Because, looking at the source, it took until 1994 for Sir Andrew Wiles to finally prove this theorem.
Right, over 350 years later.
Exactly. And to prove it, Wiles had to use incredibly dense 20th century mathematical concepts, things like elliptic curves and modular forms,
Very modern math.
things that were totally unavailable and entirely unconceived of in the 17th century. And the source even mentions that the legendary mathematician Gauss, a giant in his own right, famously doubted several of Fermat's claims because he knew the tools Fermat had were too limited. So, was Fermat just bluffing to make himself feel smart?
It is highly likely that Fermat was not bluffing maliciously,
Okay.
but rather that his supposed marvelous proof contained a fatal logical flaw that he simply didn't catch.
Oh, so he made a mistake.
Probably. He likely thought he had it, perhaps using a complex variation of his infinite descent method, but missed a subtle error because he lacked those modern algebraic tools. Gauss's skepticism is entirely valid here.
So he was a genius who occasionally tripped over his own shoelaces.
Well, we shouldn't let the missing margin proof detract from the sheer scale of his intellect. The 20th century mathematician André Weil made a really critical point about this.
What does he say?
He noted that while we might not have that specific proof, what we do possess of Fermat's methods is remarkably coherent. Weil argued that Fermat's surviving work remains the absolute foundation for the modern theory of curves.
Oh.
So whether or not that specific margin note was a mistake, his broader mathematical instincts were unparalleled.
Okay, so his theoretical number work was legendary, if occasionally flawed. But I want to shift gears because his genius wasn't just confined to abstract numbers on a page. The source material details how he applied math to messy, real-world problems.
Yes, and this is where we see the birth of modern probability.
In 1654, Fermat started corresponding with another mathematical heavy hitter, Blaise Pascal. And they weren't debating ancient Greek texts anymore. They were trying to solve a problem brought to them by a French writer and professional gambler known as the Chevalier de Marais.
Right. The gambler had stumbled onto a statistical anomaly that was costing him money, and he just couldn't figure out why.
The puzzle was this. The gambler knew from long experience that if he bet on rolling at least 1 6 in 4 throws of a single die, he would win money over the long term.
The odds were slightly in his favor.
Right. But if he bet on throwing at least 1 double 6 in 24 throws of 2 dice, he lost money over the long term.
Which deeply offended his sense of logic.
Completely. Because, to the gambler, 4 throws is to 1 die, what 24 throws is to 2 dice.
The math seems straightforward.
A single die has 6 outcomes. 2 dice have 36 outcomes. 6 times 4 is 24. The ratio is identical. It feels entirely proportional. So why was that second bet a loser?
The gambler was making a classic human error. He was applying linear thinking to a combinatorial problem.
Linear thinking.
Yeah, human intuition is just terrible at grasping exponential probability. We assume that if we multiply the variables evenly, the outcome scales evenly. But dice don't care about our intuition.
And Fermat steps in to prove it.
He and Pascal mapped out the exact mathematical landscape of chance. They showed that the probability of winning the first bet is about 51.7%.
A narrow win.
Right. But the probability of winning the second bet drops to roughly 49.1%, a narrow loss.
It's so close, but it matters.
Fermat provided the rigorous mathematical proof explaining exactly how those odds shift. He did it by calculating the probability of the event not happening and subtracting it from 1.
That's brilliant.
By doing this, Fermat and Pascal essentially co-founded modern probability theory. They took the unpredictable chaos of a rolling die and proved it was governed by strict, unbreakable mathematical laws.
Here's where it gets really interesting. He didn't stop at the casino. He took on the physical universe, specifically optics.
Yes, light itself.
The source mentions that ancient thinkers like Euclid and Hero of Alexandria understood the basic geometry of reflection, that light bounces off a mirror at the exact same angle it hits it. But Fermat tackled refraction.
Refraction being how light bends when it passes from one medium into another, like from air into water or glass.
Right. Think of looking at a straw sitting in a glass of water, The straw is broken or disjointed right at the waterline.
And I've all seen that.
Fermat wanted to know the mathematical rule governing that bend, and he refined this into what's known as the principle of least time. He stated that light travels between 2 given points along the path of shortest time.
This is such a profound conceptual shift because we are taught that the shortest distance between 2 points is a straight line.
Always.
But Fermat realized light doesn't care about distance. It cares about efficiency.
I love this concept. It's exactly like using a modern GPS navigation app on your phone.
Oh, that's a perfect analogy.
Yeah, like when you plug in a destination across town. The app doesn't just draw a straight physical line from point A to point B. A straight line might take you through a mountain or straight into bumper-to-bumper rush hour traffic.
Nobody wants that.
Right. The app dynamically calculates the route that takes the least amount of time, steering you onto the highway or down back roads, even if the physical distance you drive is technically longer.
And light does exactly the same thing, because light moves slower through dense water than it does through thin air. So, to get from a point in the air to a point underwater as fast as possible, light will stay in the fast medium of the air for slightly longer, traveling further linearly before sharply bending into the slow medium, the water, to reach its destination.
Light is optimizing its commute.
It is breathtaking. If we connect this to the bigger picture, whether he was looking at the random events of a gambler rolling dice or the physical propagation of a light wave through a medium, Fermat demonstrated an uncanny ability to spot the hidden mathematical architecture of the universe.
Yeah.
He proved that nature optimizes itself, a concept that evolved directly into the fundamental principle of least action in modern physics.
But Fermat's discovery about light created a massive new mathematical problem, didn't it? If you want to find the precise path of least time through a curved lens or calculate the exact tipping point of a probability curve, you can't use static algebra.
No, you can't.
You have to measure a path that is continuously changing direction. You have to measure curves.
Yeah.
And that requires an entirely new kind of math.
It requires calculus, the mathematics of continuous change.
Historically, we are taught that Isaac Newton and Gottfried Wilhelm Leibniz invented calculus. You know, the classic story of the apple falling on Newton's head.
Right, everyone knows that one.
But the source material throws a massive curveball here. It turns out Fermat developed a method he called Adequality for determining maxima, minima, and tangents to various curves. And this method was essentially equivalent to differential calculus.
He was doing this in manuscript form in 1636, which is decades before Newton published his work.
Wait, I need you to break down Adequality for me.
Yeah.
How is finding the peak of a curve equivalent to calculus?
Okay, imagine throwing a cannonball into the air. It travels in a giant arc, right? A curve.
Got it.
If you want to find the exact maximum height of that cannonball, you have to locate the one singular point at the very top of the arc where the cannonball stops going up and hasn't yet started coming down.
So for a tiny fraction of a millisecond, the trajectory is perfectly flat.
Exactly. The slope of the curve at that exact peak is 0. Now, to find that peak mathematically, you have to draw a tangent line.
Which is what?
It's a perfectly straight horizontal line that just barely grazes the top of the curve without crossing it. Before Fermat, doing this required incredibly tedious geometry.
Drawing it out again.
Yes. But Fermat figured out an algebraic way to do it. He found a way to let a variable essentially approach 0, reducing complex geometric evaluations down to the sum of series. He was finding derivatives before the concept of a derivative officially existed.
The source says he was the first person known to have evaluated the integral of general power functions. And this wasn't just a historical coincidence where two people independently had the same idea.
No, it wasn't.
Isaac Newton himself explicitly wrote that his own early ideas about calculus came directly from, and I quote, Fermat's way of drawing tangents. Newton literally gave him the credit.
A French lawyer sketching out equations on Sunday afternoons laid the critical groundwork for the man who unlocked the laws of gravity.
It is a towering legacy, but it also comes with a deeply humbling reality check. Because for all his genius, for all his groundbreaking intuition, Fermat was not infallible.
No, he made mistakes, and some of them were highly public.
Yeah, the source mentions a specific letter Fermat wrote to Pierre de Fermat. In it, Fermat stubbornly claimed that he had discovered a specific mathematical sequence, what we now call Fermat numbers, and he confidently asserted that every single number generated by this sequence was prime.
He was absolutely certain of it.
But he was spectacularly wrong. Years later, the brilliant mathematician Leonhard Euler came along, looked at Fermat's sequence, and proved that one of the numbers, specifically the massive number 4,294,967,297, is not prime at all.
Not even close.
It is cleanly divisible by 641.
Euler dismantled Fermat's grand claim with a single calculation.
So what does this all mean? How does a mind capable of laying the groundwork for Newton, a guy who invents modern probability and spots the algebraic secrets of the universe, make such a massive, verifiable arithmetic error?
This raises an important question, especially for anyone listening right now who does deep intellectual work. It highlights the profound danger of intellectual isolation. Fermat was an undeniable genius, but he was a hobbyist operating in a silo. He worked alone in his study. He didn't publish formal papers. He didn't submit his proofs for rigorous peer review.
It's like proofreading your own essay. Because you already know what you meant to write, your brain automatically fills in the missing words and skips over the typos.
That is exactly it.
Yeah.
Fermat was proofreading his own complex logic. When you work in a vacuum without colleagues to aggressively double-check your math, test your assumptions, or point out your blind spots, you are going to miss the typos in your logic.
That makes total sense.
Knowledge is only truly perfected when it is shared, tested, and subjected to multiple, diverse perspectives. Fermat's brilliant intuition was sometimes betrayed by his stubborn lack of a collaborative community. I mean, even the greatest minds need an editor.
Well, let's bring this all together. Look around at the foundations of our modern data-driven world. The advanced calculus used by structural engineers to build the bridges we drive over.
Right.
The complex probability algorithms that dictate our global financial markets and insurance rates. The GPS systems dynamically routing us through city traffic based on the principle of shortest time.
It's everywhere.
So much of that invisible mathematical architecture was shaped by a French magistrate who just really loved solving puzzles in his spare time.
He was a man who comfortably straddled two entirely different worlds. The rigorous, practical legal structures of 17th century France and the infinite, abstract landscape of pure mathematics.
But there's one final lingering detail from the source material that I want to leave you with, something to ponder. We talk about how Fermat's most famous world-changing mathematical theorem, the one that confounded humanity for 350 years, was casually scribbled into the margin of a book he just happened to be reading.
Right, a fleeting thought that became mathematical legend.
Exactly. Well, the source also notes that Fermat's holographic handwritten will, dated March 4, 1660, survived history. It is still kept today, perfectly preserved at the Departmental Archives of Haute-Garonne in Toulouse. It's just sitting there in a vault. And it makes you wonder, if a simple margin note could define the frontier of human knowledge for over 3 centuries, what other brilliant insights, what other unsolved mysteries or hidden mathematical codes might still be waiting right now in the margins of his ordinary, everyday legal documents or his handwritten will?
Just waiting for someone to finally look closely enough to notice them.
The thought that a foundational secret of the universe might be hiding next to his 17th century property bequest is fascinating.
It really makes you want to go check the margins of your own notebooks, doesn't it?
It totally does. The next time you sit down to work on your weekend project, just remember you might be doing a lot more than just passing the time.